Okay, so today we're going to start on the disk method. Disk, D-I-S-K, for some odd reason. Oh, hey. You just decided to keep going. Okay, now you can stop. You see, I'm not even touching it right now. Okay. Come on up. Really?
Wait, I mean, we can read that.
Yeah. You're okay with this? Everybody can read it? No, okay. I know, I'm scared to touch any more buttons. All right, well, we'll go with this. Okay, so we're going to go with the disk method today. Okay, so if you remember, the volume of a disk is just pi, and I'm using a capital R for this one, and you'll hopefully see why in a second. Pi radius squared times the height, or R equals the radius, H equals the height. Or if you lay it sideways, it'll be the width, either one. Okay, so let's draw a cylinder shape around the x-axis. Okay, so we know that from the x-axis to that shape is your radius, so we'll call that our r of x. Okay, so if we decide to take a little slice of that one, that will actually give us a little cylinder or a little disc, which is really just a solid circle instead of a disc. So I don't know why they call it disc. They say circle. Okay. So that would be our delta x. Just one little slice of it. Okay, so the volume of this solid would be equal to the sum of all those delta x's when you add them all together. You can get the volume of this one, the volume of this one, the volume of this one, just add them all together. So from the sum from I equals 1 to n of pi, your r of x of some point in there, that c of I or r x of I squared, and remember your delta x. Okay. Now, if that looks familiar, it should, because it's the indefinite integral. Well, definite integral. Okay, so that means, of course, the approximation gets more and more precise as you increase the number of slices. So if you get more and more and more, it gets closer and closer and closer to the actual volume. So it becomes better as, I guess you could say, the number or delta x approaches 0. It gets thinner and thinner and thinner. You get more and more and more and more slices. You get a little better of a approximation. Okay, so volume of a solid of revolution, which is that solid going around the x-axis, goes the limit from I equals 1 to n as n approaches infinity of pi r of xi squared delta x, which just becomes your integral from a to b. Oh, already put pi. R of x squared with respect to x. Okay, so that would just be the formula we'll be using, which isn't all that different from the formula we had for the last class. Okay. Any questions on that one? Yes.
Pertains also to what we covered last class. Where is this stuff in the book? Like what chapter is this in the book? Is this just chapter 1?
Yes, 2, I believe.
Chapter 2?
Yeah. Actually, what I'll do is I'll double check the index and I'll edit the title on the homework so you can find it.
Okay.
That's just all on Canvas, right?
Yeah. You can go to the book if you want like some extra practice problems or stuff like that. All right. Okay, so in general, just kind of a general statement. The horizontal axis of revolution is just rotating around the x-axis. And that's if you have, we'll just come up with some random shape. Between some A and B. Okay. So with the disk method, all we did was take a little slice out of it for our delta x, and we ended up with our volume equals pi from A to B, with our radius squared with respect to x. Now you can do the same thing if you get that same shape and you revolve it around the y-axis. You just get that same rectangle and you revolve it, and next thing you know, as it gets thinner and thinner and thinner, it gets more and more precise, which is called the vertical axis of revolution. Okay. Okay, so we'll just get that same shape. Uh-oh. And instead of from A to B, we'll just make it from C to D. Okay, and this rectangle, instead of delta x, will just be delta y. And that revolves around the y-axis. So the volume would just equal pi from C to D. The only difference is instead of x, you'll be using y. With respect to y. So the exact same formula, just respect to different axis. Okay. Any questions so far? All right.
No.
Oh. Oh, okay. I'll leave that there. Now these next couple of pictures are just kind of visual aids. Remember, they're going to be uploaded, bless you, with the notes. So this just shows this particular function, then when you revolve it around the x-axis, that's kind of the shape you would get. So you could find the volume using the disk method. kind of the same way here, chopped off the top, but it started off with just that function. You have the radius, and then you get that radius and you revolve it around. You end up with that same shape where you can find the volume. Okay. Any questions so far? Yes.
The radius would be defined by our original function, right?
Yep, the distance from x to that function. So that would be your radius. And the only reason I'm using capital R is because when we do the washer method, you have an outer radius and an inner radius, and the lowercase r would be your inner radius. So we'll get to that in a little bit. Okay, so let's do a quick example. Well, maybe not quick, but an example. And what we want to find the volume. Of the solid formed by revolving the region bounded by the graph f of x equals the square root sine of x. And the x-axis. And we're going to limit that between 0 and pi. About the x-axis. Okay. So if you wanted to graph this, it will look something like this. Okay, so this graph to pi. So if we wanted to rotate this about the x-axis, it would really just kind of spin that way, which means we'd end up with kind of a football. Wrong, should have started there. Okay, so it'd have kind of a football shape to it. Kind of get rid of that. So we know that our radius, in this case, is f of x, or we can use that to turn into r of x if you want to. Okay, so we know that's our radius. All depends on where x is. So from there, we just plug it into the formula. So if you know how to integrate, it shouldn't be too horrible. It gets a little worse later on, but for right now, it's not too horrible. Okay, so there you just get pi from the integral 0 to pi, which they gave us already. Square root of sine of x squared dx. Okay, so the square and the square root cancel each other out. So pi from 0 to pi sine of x dx. Okay. So the integral sign is just negative cosine. From 0 to pi. Okay, which is equal pi. Okay, negative cosine of pi is -1 minus negative cosine of 0 is just negative 1, which gives us 2 pi. Actually, I think it's just my drawing is off. It should look more like a circle. Okay, so that would be your volume. All right. Any questions on that one? All right. Oh, yeah. All right. Anybody still? Okay, so we have another example. And this one is not rotated about the x-axis, but it is rotated in the same direction. So you'll kind of see how to approach those. Okay, so let's say if we want to find the volume of the solid formed by revolving the region bounded by f of x equals 2 minus x squared and g of x equals 1 about the line y equals 1. All right. So with me, I'm a visual person, so a graph usually helps me understand what I'm doing. So let's say if we have a graph here, you have your x, you have your y, you have your g of x equals 1, which is just y equals 1, and you have your 2 minus x squared, which kind of looks like a very awkward drawing, but hopefully you get the idea. Okay, so if you notice, they didn't tell us an interval. And the reason why is because we can actually figure out the interval on our own. So all you have to do is find out where these intersect. And that's your interval. Okay, so if f of x equals g of x, are your interval points. So that means 2 minus x squared equals 1. Which, if you kind of do a little manipulation, is just x squared minus 1 equals 0. A little bit more just gives you x equals plus or minus 1. Okay, so we know these intersect at 1 and negative 1. So that's what we just have to find our volume. Now once you rotate it about the g of x equals 1, it ends up looking something like this. Okay, so g of x equals 1. So it kind of gets the top half of it, and it rotates Yeah, it probably would look a whole lot better if you actually graphed it, but yeah. So it looks something like that, but it rotates around the 1 instead of the actual x-axis. So at least you know I'll never quit doing this to go draw somewhere. You are stuck with me. Yes?
Sorry.
Mm-hmm.
Isn't the left intercept point supposed to be on the left side of the...
Oh, yep, that it is. Thank you for pointing that out. So it should be actually right there. Don't know why I did that. Yep, so -1 and 1. I'll wipe this part out before I scan it. Okay, so now that we know where we're going to perform our integral, we just have to plug it in. So it's r of x squared dx. Now the thing about this one is your radius actually comes out to be f of x minus g of x. Because remember, if you have just your radius from the top of f of x to the x-axis, you'll have an incorrect radius. It's counting that entire thing as the radius. So it's actually f of x minus that g of x. Does that make sense? All right. Okay, so that would give us r of x equals 2 minus x squared minus 1, which is just 1 minus x squared. Okay, so you won't always be able to just plug it in. Sometimes you will have to kind of manipulate it a little bit, especially if it's not right on the x-axis. Okay, so we have our volume equals pi, the integral from -1 to 1 of 1 minus x squared squared respect to x. Okay, so of course we're going to have to do the FOIL method and all that other stuff to simplify that a little bit. From -1 to 1, so that would give us 1 minus 2x squared plus x to the 4th dx. And I may have to continue that on another sheet because it looks like I'm running out of space. Oh, let me leave that up for in case somebody wants to finish up. All right. Move that over. Now, okay, so that means, let me write down where I left off. X squared plus x to the 4th dx. So that means if we integrate 1, we just get x. If we integrate x squared, we get x to the 3rd over 3. So it's 2/3 x cubed plus x to the 5th over 5. And that's from -1 to 1. Okay, so if we plug in our 1s, we get 1 minus 2/3 times 1 plus 1/5. We don't really need the 1 there. minus, now we plug in our negative 1, minus 2/3, negative 1 to the 3rd power is a negative 1, so that makes that plus. And we have our x to the 5th, negative 1 to the 5th power is negative 1, so that makes that minus. Okay. So that gives us pi, and that makes that 2 minus 2/3 minus 2/3, so that's minus 4/3 plus 1/5 plus 1/5 plus 2/5. Okay. So if we want to go ahead and just simplify this the rest of the way, we'll make that 30 over 15, since 15 is the least common multiple, minus 20 over 15 plus 6 over 15, which would give us 10, 16 pi over 15. Okay. Any questions on that one? Let everyone finish up writing that. All right. Okay. So now we're going to do the washer method. Which is basically just a disk method, but when you have a big old hole in the middle. So you want to do is you want to find out the volume of that hole in the middle. So you find out the volume of the entire thing minus the hole in the middle. So it's kind of like finding the volume of a donut minus the hole in the donut, or the tire, or whatever it is. Okay, so just a graph of that. You get to enjoy some more of my drawing. And trying to see. I drew it just fine here. See if I can recreate it. So that's kind of supposed to look like.
2 crescents.
You got jokes. But yeah, it's something like that. It was supposed to look like a. See, I drew it just fine earlier, so it looks a little bit better that way. So, but yeah, I think I got lucky. All right, so it's supposed to be a. Let's say. That's horrible. All right, but it's supposed to be like just a disc with three-dimensional disc with the missing center kind of wrapped around the x-axis. If you really use your imagination and squint a lot, you can see it.
Can you show the other one again?
I know, I'm squinting really hard. I can't see
The
it.
easier way to draw it is like you do a cylinder and then you just draw a smaller cylinder in it.
Oh, you just wasted so much on me that I can't draw. Even with step-by-step instructions, I'm just horrible. I appreciate the hint, but I just don't have drawing talent. It's just not in me.
You spent more time drawing in this class than actually math.
Oh, you should see me in Calc 3. Oh,
Oh, no.
that's horrible. 3 dimensions? Oh, man.
At this point, you're already like pulling out AutoCAD or what?
And you know what? And I'll sit back and I'll spend like 5 minutes erasing, drawing, erasing. And they just sit back and